So this is my okay. Now x is my set of unknowns, which is the tangential component along the triangle. We have seen that the ui's, right. So I can write this as, so u1 dot dot dot, right. So these are all u's. Okay, so I have written 4 sets of u's. Okay, so these sets of u's are, first set of u's I can say interior, no, let's write it like this. So this is omega dash. So the first set of edges are all the edges that belong to omega but do not belong to omega dash. Fine. The next set of edges, they belong to omega and they also belong to omega dash. So the first 2 sets of unknowns have captured everything that belongs to omega. Yeah, to get H total I add incident. Yeah. Yeah, that's why we are doing, yeah, so to clarify that we are doing this breaking up. First 2 breakups is clear. Okay, so all the boundary edges, I mean the gamma prime edges have come into the second set. Now what about the third set? Third set I am going to say belongs to omega dash and belongs to gamma prime. So which edges will come over here? The same edges as the second set. Okay, we are talking about these u's are the edges, and the final set is belongs to omega prime, does not belong to, I mean belongs to, yeah, omega prime does not belong to gamma prime. So these are the ones that are purely inside the object. Okay, now so it seems that I have counted the gamma prime edges 2 times, but that's all right, because in one case the edges are representing the total field, in the other case they are representing the scattered field. But there is also a relation between the u's of the second set and the u's of the third set. They differ by incident field, right. So when I have my matrix, my A over here, so this was my x. When I have my A matrix over here, right. So again this I can break up as how many parts? 4 parts, right. So these will multiply the first set, these will multiply the second set, third set and fourth set, right. So when it comes to these 2 sets of edges 2 and 3, what kind of coefficients will there be? 1 minus 1, and the right hand side will have incident field, because these are scattered, these are total, because I am trying to represent. So what is the equation that links scattered and total? It is going to be of this form, Hs minus H is equal to, so in terms of, if I want to write it like this, it becomes 1 minus 1 Hs H. Right. So very nice way to link up the H's, right. So here you can see Hs is H scattered, that is one of the variables, H is H total, that is one of the variables. So this guy is going to come from set 2, this guy is going to come from set 3, and correspondingly the coefficients are simply 1 and minus 1, and they give me a minus Hi. No, we have to construct it, So when I do the testing, what will I do? The testing will go edge by edge, right. So for when I start taking edges belonging to gamma prime, that is when these equations will come into play. Remember, the kind of equations that I get, they will be sparse. So if I have a edge, let us say over here, this is not going to involve edges far away, those are all going to be 0, we have seen that, right. So the boundary will come into play when I have some elements over here like this. So this is, that is why, I mean, at least in the first course in finite element or FDTD, they do not talk about scattered field formulation very much, But you can see it's not that difficult. Only thing, bookkeeping you have to do that at the edge, make sure that you are taking care of what is your variable. Is it scattered field or total field? If they are different, make sure that you subtract them by the correct amount. Okay. So, your system of equations becomes a little bit larger, but it does not matter much. Okay. There are ways of being clever about it and combining set 2 and set 3 into one variable itself, but basically you are doing the same thing once you have identified this. Well, we can't independently solve it because those edges finally, like the last, look at this green triangle over here. The reason we can't independently solve it is this green triangle has edges belonging to the set 1 and set 2. So, they are not decoupled. I cannot solve set 1 completely because set 1 has edges belonging, I mean, if I look at this triangle, it has edges belonging to both set 1 and set 2. So, they become coupled equations. I can't get a system of equations purely in set 1 is what I am saying. Set 1 is purely interior, edges. So, what is set 1? Belongs to omega, does not belong to gamma prime. The first equation means which equation? This is your Ax. This is that set, there is no other set of equations. No. This is the full set of equations where the number of variables I am doing a double counting on the edge. Okay, so there is no way for me to separately find out just first set, and second set and third, because they are coupled. Yeah, there will always be one variable which belongs to the other set somewhere. So, when we try to form the system of equations, this will become even more clear, this coupling that is happening. So, is it clear? So, what has happened is the incident field, right. So, now here we can get into the comparison between the total and the scattered field, total and scattered field. So, incident field, in the total, let us call it total F, let us call it TF and SF. Okay. So, this is TF and SF. Okay. So, TF, where did the incident field appear? So, incident field appeared at gamma. If you look back here, this total field formulation, all of this has happened, all of this happened on gamma itself, outermost boundary, right. So, the total field appeared at gamma. In the scattered field, where did it appear? Where is it being introduced into the system of equations? At gamma prime, not at gamma. At gamma, nothing happened. The incident field did not appear because the scattered field was the variable. There was no chance for the incident field to appear. Okay, so do you think that this is a big difference or a significant difference where the incident field is being introduced into the formulation? At gamma prime, we will have lower number of edges. So what? Counting the number of non-zero entries in B does not really tell us anything. Is there something else that is happening? So, here is an aspect of numerical computations which you should know, that supposing I have a boundary and I introduce no object, I introduce a plane wave at one point, a plane wave source at one point. I know analytically the form of what the field should be because there is no object, plane wave. But I can choose to solve this on the same finite element mesh. I should get the same answer as the analytical solution. But will you get the same answer? You will get the same answer as you make the discretization finer and finer, because the variable is being expressed on the basis function of those triangles, right. And those triangles you saw, they were linear in x and y, but the actual field is what? Exponential, sine and cos. So, I am approximating sine and cos by linear in x and y. That approximation gets better and better as the size of the triangles is made smaller. Sin x becomes x, cos x, whatever other approximation you want to do. So, this approximation of the incident field on the mesh, is it more or less accurate as I go away from the source location? It is less accurate the farther I go away, because the errors will accumulate, as I go further away, right? Very close to where I am specifying the boundary condition, it will be accurate, because the boundary condition is right there. Fields will try to match the boundary condition as much as possible. As I go further away, the approximations, the error of the approximations will begin to grow, because I am finally trying to represent a sin and cos by linear terms, right. So, now can you answer which is better between TF and SF? SF is much better, because in TF the incident field has appeared over here on this boundary, then it has to numerically propagate to the object and get scattered, right. But in the scattered field, in the system of equations, it is being introduced on the surface of the object. There is no what is called grid dispersion, right. So, this term is called grid. Another term that we will encounter in a finite difference time domain. So, the incident field, I know it analytically, but once I put it into the system of equations, it is a system of equations. They don't know what the form is anywhere else unless I give it to them. So, the scattered field has this advantage, okay, that it appears directly at gamma prime. What else can you think of? So, okay, this is the main advantage of scattered field. The other advantage is this. Let us say that we have spoken about this radiation boundary condition being inexact, correct? And it is inexact when the field that is hitting it is non-normal, not coming at 90 degrees, then something reflects back, correct? Now, as an engineer, if you wanted to make that situation better, okay, so let's draw it once over here. So, this is, okay, so right now it does not matter total field or scattered field, some wave has come over here. This is true in total field or scattered field. Even in the scattered field formulation, I am imposing the boundary condition, the RBC, which is correctly true only for normal incidents, not for non-normal incidents, right. So, some amount of this is going to get reflected. Now, as an engineer wanting to reduce this, what other option might you do? This is reflecting, this is the numerical reflection. Why? Due to inexact boundary condition. Okay, I want to reduce this. So, what do I do? Transpose this situation into a real life situation. Real life situation, you have an antenna here, okay, and you don't, it's sending out some fields, you don't want the fields to come back to you, basically. That's a reflection. I want to cut it out. What would you do? Supposing I can't increase the boundary. I mean, I'm in a room, I can't make my room bigger. Put some absorber. If I put an absorber, then nothing will come back to me. And we already have seen examples of this, right? If you go to acoustic chambers, anechoic chambers they are called, it's a very funny thing because nothing is reflecting from the walls. It feels very, I don't know if you've been inside any of these rooms, nothing comes back to you, right? So, that is physically creating a absorbing situation. All microwave and radar studies, if you go to their labs, they have these anechoic chambers where they, if you want to characterize a antenna, you don't want some spurious reflection from the wall. Supposing I do a measurement in this room, I am trying to measure the radiation pattern of an antenna, but without realizing something is hit the roof and come back and my measurement is corrupted by these reflections. I want to cut it out. So, what do? I fill the room with I line the wall with an absorber. Okay. So, this was an absorber in real life. Can I make an absorber mathematically? Put some extra padding, alright, fine. And how do I implement mathematically an absorber? How physically you are saying measure the field, but mathematically what do I do? So, now you have to use the word compute, not measure. But how do I compute without solving the system of equations first? And once I solve it with an inexact boundary, I don't know, I mean what I've got is everything put together, reflections, everything put together. So, and let's go take the intuition from the physical problem to the mathematical problem. Physical problem, I put some layer over here which absorbs. Absorbs means the first word that should hit your mind from your undergrad EM course is skin depth. What is skin depth? If you have some conductor, wave goes inside, it gets absorbed and dies after skin depth. But what made that property to have different levels of skin depth? The loss in the medium, right? Conductivity basically. If there was no conductivity in the medium, what would happen? Would there be any skin depth? What is the skin depth of vacuum? It's an absurd question. The skin depth is infinity. The wave never decays in vacuum, right? Vacuum has no loss, it goes on forever. The moment I introduce some loss into the thing, that is conductivity, the wave begins to decay. So that's the hint. How do I implement this absorber mathematically? Well, I just create in this green shaded region, I introduce loss in the epsilon r mu r of those triangles. So over here, I can say epsilon r, make it lossy. Exactly, epsilon r will become complex. In free space, epsilon r is 1. Now what I will do is I will make it 1 minus j something, right. So this is one way of implementing it. So what will happen now? Even if the wave comes at a non-normal direction, what will happen? Some part will still get reflected, right? If you look at your reflection coefficient, Fresnel reflection coefficients, there is going to be some, as long as there is a difference between n1 and n2, between two mediums refractive index, some reflection happens. But that reflection I can control by controlling the refractive index of this green region, right. So that's the sort of intuition over here. So this is hopefully less. So this is one way of improving boundary condition, okay. And in this course we will look at further on specific examples of these absorbing layers, as they are called, okay. The most successful and popular way absorbers are called PML, perfectly matched layers, and we will talk about that subsequently in the course, okay. But it is an example of an absorber. It absorbs the field and does not reflect back, okay. All of this having been said, do you see any differences as far as absorbers go in total field and scattered field? So I have put an absorbing layer because I wanted to improve boundary conditions. Very good. When I go to implement this using the total field formulation, what will happen? The place where I introduce the incident field will not change. It has to be on gamma. Now this gamma has to travel through a lossy layer. So I will get further errors in the propagation of this wave. It was bad enough to propagate it through vacuum, but now it has to travel through this lossy layer. The source is outside, let's say some radar far away. Think of it like that. So I have no control over where the source is. But now if I introduce a lossy layer, incident field continues to be at gamma, nothing changes, right. If I look at my total field formulation over here, well, let's look at the right hand side over here, right. So whether total field or scattered field, the left hand side term is the same, right. Your material properties are entering here and here. So the fact that I have now introduced some lossy materials here does not alter the left hand side of the equation, right. So that incident field will have to travel through this lossy layer in order to get there, right. So in terms of absorbers, the total field has more errors due to propagation through absorber. What happened to scattered field formulation? Perfect, no change at all, because incident field is being introduced at gamma prime and your absorber is far away. In fact, it made everything improve because the scattered field would be absorbed even better. Incident field suffers no degradation in propagation across the mesh, right. So, that is the win-win situation over here. So, there are two strong advantages for scattered field formulation. Over here, okay. You can improve the boundary condition and no errors in the field propagation, okay. So, given a choice, it is easier to code total field formulation. So, many times that is the first thing you would code, and that is useful like as a reference solution. Then if you want to actually use your code for some serious work, it is better to switch to scattered field formulation, because then you can keep improving your boundary condition, right. Adding a absorbing layer is trivial. What is there in code, right? You just have to introduce some loss, okay. And this design of these absorbers is another separate area of research altogether. You know that if you introduce a loss abruptly, what will happen? You will get a strong reflection. So, there is a lot of art in this, make the absorbing the loss component gradually adiabatically increase from the boundary. That makes the reflection to be very, very less. So, all of these things are tricks used in physics, electromagnetics to make high quality factor resonators and so on, but that is a separate topic, okay. So, what we have done is that we have spoken about. So, we started with the kind, so actually this is a good thing, we started with the kind of shape functions. These were our vectors in space. Then we took our equations, converted it to weak form, and we spoke about our boundary conditions, radiation boundary condition, which is applicable only to scattered field. And then we chose the two variables, either total field or scattered field. These are two different ways of solving the problem, right. Okay. Any questions? Yeah, because the computational domain is ending at gamma. That is the place where I do not want any spurious reflections. So, that is the place where I apply the RBC. Yeah. The triangles near gamma are where I will begin to impose a loss if I were implementing a absorber. Incident field will undergo further distortion. Yeah, in the total field formulation. H incident is defined to be the field in the absence of object. Yeah. It has to travel through the absorber, right? Because in analytical form, I am defining it only on the outermost boundary. The rest of the propagation, which we are not actually doing, but the equations are doing it. The information of the incident field has to reach the object in order to scatter. That is happening mathematically through the mesh. Automatically, we are not doing anything to it, but when we impose Maxwell's equation, that is what is happening. But now those incident fields they are anyway getting distorted by the mesh because of the approximation of basis functions. They get further messed up because of these absorbing layers. What will be the value of H incident inside in omega, in some interior? What will be well, you would have to calculate it. You are telling in your system of equations, you are telling the value of H incident only on gamma. You are asking what is H inside at some point. What are you asking? H or H incident or H scattered? H incident, that we know analytically. In the whole domain we know. But that does not enter into the system of equations. The system of equations accepts it only at gamma in the total field formulation. How does it enter? Because it is e to the minus j k dot r. What value of r are you putting? Only boundary edges, nowhere in between. The left hand way, I have spoken only about the RHS so far because that is where some amount of subtlety is there. Next, when we talk about putting everything together, we will come to the left hand side and put it. So, that is the last part, which is putting it all together. We will look at left hand side, we will look at right hand side and assemble a system of equations. So far we have been concentrating on the boundary because that's a more sort of critical, crucial part. Next, we will look at the left hand side.